Okay, after this introduction to least square estimation, we came back to the processing of the GPS data. We are at the point that we have seen that the double differences is one of the most used observable of the GPS, because it could reduce a lot of common error in the GPS observation. We have already seen that we also perform, so it means when we speak about double differences, that it means that we are computed the component of a baseline, a vector connected to receiver. And at the end of the analysis, we are going to estimate this component, in fact. And we have seen that usually we have a lot of station and a lot of satellite, and we observe for many times, we have many epochs that we can process together to obtain our final solution. So we have a redundant observation. We can the least square, for instance, method to estimate the parameter and the precision associated to this estimation. Okay, now we have seen what is a least square estimation in a general term. Now we are going to see how we apply this method to the GPS. Okay, so you can follow the lines that I'm going to follow in my presentation. So this is the equation, and in the equation we have a term. If you consider that you think that the baseline is short, so the stations are at a distance less than 30 kilometers. So if at the moment we forgot a lot of error, otherwise we can introduce other parameter. It's just to simplify at that moment the expression. So we have a term related to the geometric part, the distances between receiver and satellite, and we can write this in terms of differences between receiver A and receiver B. And we also have a combination of ambiguity. So these are our unknown, we can say. Our unknown are inside. So, we have our unknown in the distance. But what we can see, because the distance, we have an expression related to the square, no, not to the square, to square root, sorry. I started the to the square root of the distance as a coordinate, and we have not a linear relationship between observation and parameters. It's not linear, so we have to deal this problem. Up to now we have seen what we have with a linear relationship between unknown and observation. And we are not in this condition. To solve the problem, when you have a non-linear relationship, not a linear model, you have to linearize your model using a Taylor expansion, step to the first term. And so you need some approximate values. Okay, do you need, have you got any problem? No?
Model is the A matrix.
Yes, it was the A matrix, but the A matrix, we have seen that so we cannot write sorry, there was already in the blackboard a relationship like this. This is a linear in terms of vector, a matrix of the linear model. We can, at the moment, with the GPS, starting from the double differences and so on, we cannot write this type. It's not a linear model. So we have to linearize our observation equations. So we can compute, we can use approximate values, and I use this symbol to say that it's being computed using approximated values. So we have the distances, computing the approximated value divided by the wavelength to have the phase, and we compute the derivative with respect to the unknown quantity. And we compute this in the approximate values. And okay, it's quite easy to see how we can obtain this relationship. Have you got any problem? I think no. You know. Okay, you can see we have a distance, and we have something like this. So we have to calculate the derivative with respect to this coordinate, and we have this quantity. Okay, is in terms of vector to simplify, but so you have to see for each component. And one, I mean the satellite, two means the number of the satellite, of course. And so at the end, you have a linear, you can find a linear relationship between the observation and the unknown parameter. Now the unknown parameter are this quantity. That means a correction with respect to the approximated values. So you have approximated values for the coordinate of the point. And you have this because the GPS, okay, if you have, in general, the GPS give you coordinates, has been set up to give you your positioning in real time. So you have some information. And if you, also during the measure, you see your coordinates. So these values are computed in real time using code observation. So we can, they have a factor of error and are precise of the order of some meters. It depends. I don't told you that the precision in the planimetric position is higher than the precision in the height component. Why? Because we have seen that we have problem with a lot of things that are related to the height. For instance, the troposphere and so on. The planimetric position is more constrained than the height, because it's really related to the number of cycles. If you have done an error, this component. And so you can use very approximate coordinates that you receive by in the file of the data. At the beginning there are some coordinates. Okay, but you can also have more precise coordinates, because probably you have already made a measurement of this benchmark, so you know the precision of this benchmark with a centimetric level and so on. So that you can also use these approximated values. And when you linearize your equation, you are going to estimate the correction to these approximate values. This quantity is the differences. Probably, I don't know if I write. No. Yes. Is the differences between the real coordinates of the point A and the approximate values of the point A. Okay. I am speaking about vector. So x means the position of the point, x, y, z, we are not separating, okay, it's a vector. So I use the x but to say the positioning vector. Okay, so we are going to estimate this quantity. At the end, of course, estimate vector will be the approximate values plus the estimate correction. If you remember my convention, This is for approximate and this is for estimated. You have seen, we have seen in least square presentation. Estimation, approximated. So when you use when you compute, wait in a minute, you are writing. Now this is important, this point.
I'm really confused about approximated and estimated. What's the
Approximated means that you know in some way some values. So I know that Trieste have a latitude of, I don't know, which is, I guess, a latitude of 46 degrees. Okay, I need more digit to say, for instance, I don't know. My point have a latitude of and so on, because I already made the measure of this benchmark of, or because when I started my observation, the GPS give me this information, but it was approximate information because they obtained this approximation in real time using code observation, not without all this huge with this important analysis of data.
A sort of preliminary data?
Yes, approximated is like a preliminary, yes.
Okay.
Approximated means that it is close to one value, but it's not the values, the real values. It's an approximation. And so we know, but it's important to linearize. So I know that, okay, if I use coordinates, approximate coordinates obtained by just the code measure in real time, I know that I can have 3 meters of error in the planimetric component and 6 meters of error, for instance, in the high component. I can start using this approximate coordinates. What happened? That these are quite far from the real position by meter. So in the nonlinear least square estimation, we have to do an interactive procedure. So now we start with a very approximate coordinate. We arrive to estimate this correction. After I can correct the approximate values. And I can start another step in my iteration method using this as approximated values. And the solution comes to converge at the precision that you want to use. So the least square estimation, starting from a linear model, is a correct estimation. You arrive just to one, given this type of measure. This measure, and given this stochastic model, I have just one solution. Okay, with a not linear estimation, the solution depends on the approximate values. And so you use an interactive procedure and you stop when the precision, the change in the a posteriori variances, or you can see that your parameters change a few in the last decimal digit. I forgot it doesn't change, so you say, okay, I can stop my iterative procedure because I'm converged to the real solution.
It's a sort of an inversion of the data. I mean, we have the first data that is the approximated one. After that, we have to converge to the real data by...
it's an iterative procedure, it's not an inversion. It's an iterative. You go to the solution math, you use a lot of this type of procedure we use in math, Okay, how you can prove this theorem? You use this iterative. You start from, you have to converge to the solution. Inversion is often and not linear problem, so you have to do iteration, but there are two different things. Iteration is I go to the best solution step by step, improving my results. And inversion often is not linear problem, so you need this approach. So
this is like a root finding.
yes, yes.
It's recursive or iterative.
Recursive, recursive. Sorry, in English, recursive. Yes, recursive. We use different also. Okay, recursive. Yes, yes. Step by step, I'm going to improve my. Yes, I think that. Okay, you can use this to turn. So we have now we have a linear problem. So it's dependent by your coordinate a priori coordinate. So when you purchase data and you have a new network, you are going to improve step by step your coordinates. So you start, for instance, from the approximated coordinate that you obtain by the raw files, the files that you obtain by the campaign, and after you, for instance, you correct the data for the clock biases, so you have improved your solution. After you correct the data for the cycle sleep, so you have improved your solution using typal differences. After you fix the ambiguity, so you improve the coordinates. After the last run is when you want to estimate, you have all improved all this quantity, and you try to arrive to the correct solution, correct in terms of the precision that you fix. So often when you purchase data, you have to improve this a priori file. So you need to give to the software a priori file with the coordinates. With this reason, because we are not computing a linear least square estimation, we have a non-linear problem, so we have to linearize our problem. And the software asks us, give me a priori coordinate file. I say, why I have to give you the coordinates? I want to know the coordinates by this processing, but it's just approximated values.
So
Yeah.
in this nonlinear approach, we are both trying to find the parameters and the position?
Yes, together. Yes, we can also have a mixed part in the equation when we have a part with non-linear and a part with linear. You can solve together all this. You have to linearize the parts that are not linear, of course. And, okay. In fact, this is that we need to compute linearization, so we need coordinates, and we can use a pseudo-range observation. So, looking at this equation, what we have, we can see that we have our observations, the double differences in terms of distance, minus the distance, the approximate distance that we obtain when we linearize this equation, and this is equal, this quantity, this difference, to the baseline correction due to the a priori value. So what we are going to estimate is the baseline correction we have seen by this equation. We are looking at the baseline, the component, not just the single component. We are performing relative. So no, it's not here. Yes. at the beginning we have seen that we have a relationship by the double differences we obtain the baseline component. In this case, the baseline component, the correction to the baseline component. And okay. So at the end of this, we can, when we arrive to this equation, we can obtain the baseline component as the combination of ambiguity. And okay, we have seen that if you have many satellites, you have a rule that we use the number of dependent double differences that we can set up. The same when you have more receiver. If you have a network of a receiver, there is only one n-1 independent baseline that you can build. So you have n receivers. The total number of baselines that you can build is n multiplied n-1 over 2. Yes, over 2. So you have to think that if you have a square, no, if you have 4 receiver, sorry, how many baselines you can create? 1, 2, 3, 4, 5, 6. So using this, you have 4 receiver. The total baseline are 4 minus 1. That is means 6. But the number of independent are 3. Independent. Okay. This is important. Okay, you can see in this slide why. As we have computed with the double differences, easy. If you compute, for instance, using the x component of the baseline AB, and you consider the baseline AC, if you have a triangle, the number of independent baselines are 2. In fact, this baseline, for instance BC, is given by a combination of the other 2. So that means that if you ask to the software compute all the baseline, so you have a problem when you want to invert the matrix, the normal matrix in the least square, because we have determined equal to 0, non different by 0, so it cannot perform the inversion of this matrix. So we need just independent measurements, and this is important because now we are going to see what the different type of GPS software, processing software. There is a big distinction between commercial software and scientific software. The commercial software use single base positioning. The other one are multi-base positioning adjustment. It means that baseline for baseline, in the single base positioning, we take just any singular baseline and we process this singular baseline. In the multi-base adjustment, all the independent baseline are processed together. And from this, we obtain the coordinates of the point. We have to see how from the baseline component we obtain the coordinate. We are going to see. But it's important that in the single base, as the name, the software processes baseline after baseline, not put together. So it's a simplification. we are going to see later the other is a simplification, because we don't take, we have seen that least square is made by the functional model, design model, a stochastic model. And if you take into account, if you use a single base adjustment, you don't take into account of all observation and the correlation between the observation. So if you have, for instance, a square, we can build 6 baseline, and okay. So you can process every single baseline in the single base processing, but at the end it's not correct, because you have to process just the independent. We don't have any numerical problem, but at the end we obtain results that are not correct, because we need just independent, otherwise you are using the same data to compute not in linear independent observations. So you have, it's not correct from a statistical point of view. So, but in this case you process baseline after baseline. So to compute this coordinate, you don't, we are going to show you. In the multi-base adjustment, we take, for instance, these 3 baseline, and we process together these 3 baseline. So with me, it means that the deterministic part of the design matrix of this point, there is a relationship between this point to this other 2. And also in the covariant matrix, we take into account the correlation, especially in the result. Probably we can know the correlation between these, because we are using the same satellite, so we know the relationship between the observation. But in the result we have a covariant matrix that is full. We have precision and also correlation. So just to say, we have this square. We can, and we have 4 receiver. We can compute these differences, double differences, but these double differences, we can compute the baseline component, and from this baseline component, we are going to see how we can obtain the coordinates of the point. In the multi-adjustment, we use this, for instance, these 3 baseline together, or we can also use the other 3, but not all together. Just 3 independent one. So in the approach of single base, we compute this baseline A, D, DC, and we have the covariant matrix of this baseline. So okay. For instance, we compute in a single single base processing this baseline, and this baseline, for instance. So we want to know the coordinate of A. So we have 2 observations that give us the coordinate of A, because we have the baseline, for instance, B. Now we are thinking with the X component of the vector, but also I can write all. So, for this baseline, okay, so it means that the X coordinate of the point A is present in this observation and in this one. So we need to combine this observation using another step of the least square adjustment, least square estimation, because we have two observations that give us as related to this coordinate. So we use least square to compute the baseline component. From the double differences, we want to estimate the baseline component. When we obtain the baseline component, we want to estimate the coordinates. You understand? You can do this also in one step, but usually the single base adjustment do this in single step. So we purchase a baseline, we purchase another independent baseline, and so this when I write this component, it means that it is xb minus xa, and the same when I write this mean this relationship, no? So we have the quantities that we want to estimate in two equations. This is a value that we have estimated. So how to solve this? We have a redundant observation. We can compute the least square, but it's a least square where the covariant matrix is a diagonal matrix. Along the diagonal, there are any singular covariant matrix coming out by this single processing. When you use a multi-baseline approach, you have a full matrix because these three baselines has been processed together, starting from the double differences. So at the end, we have all the components of these three baselines and a full matrix of covariance. So it means that in this computation we take into account for correlation between data. And the data are being correlated because they are measured in the same time, so they are using the same satellite, so are in the same atmospheric condition, for instance. They are really use the same data because to compute this double differences for this baseline, probably you use the same phase measure that we use to compute this one. So these are really correlated. We are using the same data. You understand? So a scientific software like okay. A scientific yes.
I have a question. We want to estimate the coordinate of A, so we want to use delta xab and delta xad, but we have only two equations with three variables.
Yes, we now we have to, yes, it's a correct your observation. Now we don't speak about reference frame. We have a rank deficiency in this problem. I'm going to show you how to fix. Now we have just a relative measurement between, but if you want to estimate coordinate, you need to fix the rank deficiency, it's called. You need to fix, for instance, the coordinate of 1 point. So you can obtain is a relative, is let's example, I know the differences in the height between me and you, and to fix the really height, I have to know one and the two height. Okay, we are going to see. Okay, yes, but your observations is important. In fact, I say from the double differences we obtain the component of the baseline. From this we want to obtain the coordinate. We are going to arrive how we can obtain the coordinate. We have seen that we can use least square with different approach, but it's true. At the moment we have some problem with, and we have a problem around deficiency. In fact, there is a slide after. I want to say that I skipped this slide before, but in this slide there are presented the most used scientific software to process data. So as you can see, most of them are using double differences. Or sorry, it mean Y, Gypsy. When I look at the slide in my PC, I didn't see all this arrow. When I see in a bigger way, I see Gypsy. Okay. This is yes. These are the most used software for geophysical application. So you have precise point position is not a new technique, because people from Gypsy use these techniques by all time. But now that we have precise point position, means that you don't need a relative positioning. So you don't need to connect a station with baseline. But I don't know how it works in the past. Now it's quite clear. We have a lot of global model about ionosphere delay, troposphere delay, and so on. So you can correct your data also using this model. So it's now we improve really our capability in precise point positioning. This option is also present in Bernice and Gamut, but I don't really know how they can obtain the same precision that we obtain with Bernice and Gamut. I can use Bernice and Gamut. And okay, probably they change. I don't know if Bernice now run also under Mac or this. I didn't check. The important thing is about the cost of the program, the software, because no, the important thing is about the quality of the program. There is a lot of paper about the comparison of this processing of this software, and we obtain the same result in terms of velocity of point. Of course, if you look at the single solution day by day, you have some differences, but at the end, when you want to obtain the velocity of the site, this software gives the same result, so are equivalent. Now, okay, Bernice is developed by University of Bern in Switzerland, and also for scientific application, it's quite expensive. And if I remember well, but it's a long time that I didn't buy this software, you can also spend 8,000 to 10,000 euros, so it's quite expensive. And for scientific educational scientific application, yes. Gamut is free. It's provided by University of the United States, by Massachusetts, by university, if I remember, and yes. And it's free. Okay, in the last year there was a student from Cuba, and the people from Cuba in the past cannot use this software, cannot have access for the embargo political decision of this country. So, but I think that you don't have problem of this type. You are from Ethiopia. No, I think that it's better. In fact. No, it's a problem because you are in a developing country and you don't have so much money to buy a software, and you cannot use a free version. So sometimes the visiting scientists use the software that we have here. We cannot give, of course, the software, but they can use the software installed in our PC. laptop server, of course. So these are the three software. I don't know. It depends on your feeling. If you want to go to see how you really can purchase GPS data, we can have at the end of this lesson some more hour when you finish all the exam, all the courses. I know that in April you will really stress about all the program and you want to start to think about your dissertation or the application for the next year for PhD program and so on. If you are interested, we can see the processing with for instance, for Gamut, because at ICTP we don't have Burmese. But it depends on you. It's a software, so as you use a software, you have to know how to use this. I want to show you. I don't know if today or tomorrow. No, today it's not ready. I want to add some slides in this presentation to show you all the files that you need, because when you check the list of the file of information that you have to give to the software to purchase your data, you find all the things that we have seen. The a priori coordinates file, for this reason, because we are dealing with a not linear model and the square linear model. You find the file for ocean loading parameters, the file for the file center variation parameters, the file for the orbit, all the things that we have seen that was quite boring to see how many errors you can have in GPS, but you have to give this information to the software, and some information are correct for a long period, other one you have to check periodically to see if there are some upgrading and so on. So now I'm going to finish, there are some important parts of the course about the GPS and series analysis, and we have to talk about SAR, so we don't spend time in this practical, sorry, I put my phone back. And okay, but if you are interested, we can decide to meet again and do some exercise. So I know that this part is quite difficult, because it's a typical. I'm using the last year. I'm using an approach that we use for some surveying techniques. It's a deformation because I'm teaching to students from engineering, so we need and they are studying topographic survey. So I use this type of approach, but we can also see in a very easy way. But I think that I like to show you all the steps. I can understand that it's the first time could be a bit dispersive to see all the steps. Also the network problem with independent observation. But is a problem that when you have a software, now this is important, I want to say you this before, but I forgot it. Okay, the scientific software know that they have to use independent double differences and independent baseline. So when you give the station the file and with the raw data, and in any file corresponded to a benchmark of your network, the software can ask you to connect, to create the baseline. This is really in Burmese, is really clear, but I think that you can do the same in Gamut, I don't remember well. But you can say, okay, I want to create this baseline, I want to process this one. And when you do this, you have to be very careful. You have to remember the rule n-1, the number of independent baselines that you can create. Otherwise, the software gives you an error message. The first time when I was a student of my master's degree, and I was starting to process GPS data, I did this mistake. I close a loop, and the software say no, you cannot. So I have to understand the message. So it was related to this problem. And you can also ask to the software to create baseline automatically, and you can choose. In Bernese is easy, but I think probably in Ghent I have to check. I know better Bernese because I use this software for a long time. And you can say, okay, create a star. So if you have a if you have a nectar with the station, you can say, okay, this is the station that I want, and you can connect all this station with this point. Okay. Or otherwise, you can say connect point to have a the shortest baseline as possible. So why the shortest? To reduce the common error, a lot of tropospheric error and so on. So you don't have this connection by this one, for instance, and so on. You have to, the software will be careful to not close the loop. Or you can ask, use create the baseline with the maximum number of observation. Okay, when you have permanent station, more or less you have the same observation. You can have a station that can observe a lower number of satellites for some reason, because there is a mountains or something like this. This is important when you have a session of measures, so you observe for 5 hours in a place, after you switch off your instrument and move to another place and switch on the instrument and so on. In this type of campaign, so it's important that you have the bigger number of observations that you are going to process, because you want redundant observation in your least square. So you can choose this, and often the software can do this in automatic way. But in some software you say, okay, but follow this criterion to find the network connection, the baseline. Okay. Because we have to, oh sorry, this we have to switch to the other presentation, because in this lesson sometimes I don't fit exactly the lesson, and in fact it's strange that we finish in this way. So if you look at the examples that we have seen before with this 4 point, we can write 3. Okay. Now I think that this part we can skip, because it's very good for engineerist applications. I think that this year I know that it can be some confusion in your mind. I switch it to another because to solve the problem. No, I think that is not a good idea to show you this one. Sorry. It's really used for some way application. Okay. This one is important. Oh, full screen mode. Okay. So, with the relative positioning, we compute baseline component. That is the differences between coordinates. So now we want to obtain the coordinate. So we have the same example with the for receiver. We have a for benchmark, and for each benchmark we want to know the coordinate. So we have to solve the rank deficiency problem. It's like when you have all the components of the baseline. It's like you fix. You have a rigid body. I know the relative distance between one point to another point, but we don't know where is in the space. How is fixed, how is rotated. We have just the relative position. So we have a rigid body, so we know the dimension of this body, but is free on the space. Now we have to fix this one in the reference system. A reference frame is better. So we have a problem of rank deficiency equal. And there is a okay. The simple way to fix the rank deficiency is fix the coordinate of a known point. For instance, reference point given by the reference system, the reference frame. Sorry. For instance, from ITRF. If your network if this point, for instance, is a reference, is a point of a reference frame of the reference frame, but sorry. So if you have a network of 4 points and you want to know the we have computed by scientific software this baseline, and we know the component of this baseline. Now we want to know the coordinate of these 4 points. We have a problem because we have 3 equations for each component. 3 for x, 3 for y, 3 for z. And we want to know 4 for each component parameters. So we have to fix. We have the relative. We have seen that we know the relative position, but one method to fix this problem is, for instance, fixing the coordinate of a point. Why? Not the coordinate, for instance, of a reference point. So in your network, in a geophysical application, but also in surveying application, you introduce in your network also some reference point. For instance, station from the ITRF network, or for the upgrading in your country, because ITRF is global, but in your country you can have more stations that are framed in the ITRF, and you can use this one. For instance, we have an improvement in Europe using a more dense network called UREF. EUREF network that is correlated to ITRF reference frame. But in more dense, we have more station because it's easier to use, because you have closer station to your network. So the classical approach is to fix a number of reference frame parameters in the processing phase, or to apply time constraint to normal metrics in order to remove the singularity. Okay, now we are going, this is very theoretical, we are going to see an example. For instance, the gamut software used to fix the reference frame, so to compute the coordinates of the point starting from the baseline, use a loosely constrained solution. It means that we started to say, okay, the coordinates of satellite are known, so we don't have to estimate this coordinate. In the gamut approach, they compute also the position of the satellite, but they know, they have the ephemerity, so they know, have a good approximation of this estimate. But they have this loosely constrained. They constrain the satellite and the coordinates of some reference point on the Earth of the ITRF network, and every time they are going to find the best solution according to the observation and this constraint of the orbit on the coordinate. But they estimate everything. So, okay. At the end, they also, after this, when they compute the baseline, they use this loosely constrained approach. But at the end, you can fix the coordinate of some point of your reference frame to have your fixed solution. There is a different step in the processing, in this data processing. And at the beginning, they loosely constrain, they don't fix anything, but give a different weight. We have seen what is a least square estimation. The least square estimation, we have the cofactor matrix, the weight matrix. And it depends on the values on this metric. I can constrain or not an observation. I can say, okay, this parameter, this observation for me is more reliable than another one. So we give different weight. Also to the a priori parameters. Okay, there is some method to loosely constrain, uses this weight of the observation. But it's important that doing this, they reduce the risk of introducing in your solution some error due to some a priori information that you give. If you have problem with the orbit, you are not to introduce this error in the solution, because you can check estimating again these parameters. More or less this. And this is during the processing, when we are estimating the baseline. At the end, you need to fix this coordinate to reference frame. So at the end, you are going to loosely constrain the coordinate of the reference point. It means that, okay, we don't fix this coordinate, but we give a very high weight to this one in the least square adjustment. So it's not fixed, but is really constrained. The solution is quite constrained to these values. But I can check the residuals of my least square estimation. I can see that in that day there was some thing that my solution is too far from the theoretical solution. So from the solution predicted by the ITRF file of the coordinates. Do you remember ITRF reference frame is a set of coordinates and velocity at a given time. So I can, if I have a point that belongs to this network, I can predict which will be the theoretical values, and I can check my daily solution with this one. Okay, so we have seen the loosely constraint method of using, especially by gamete software. In the Bernese, we use a different approach. They use a different approach. They use usually you have a network of station more than 4 stations. So in this network, you have to introduce different reference stations. Different stations that belong to the reference frame. And in this case, you, in the computation, you don't fix the coordinate of this station, but you use weight for this coordinate. You fix the orbit, so you know that the orbit of the satellite are in a well-defined reference frame, because we have seen that in the file you find the note about the name of the reference frame. Do you remember? Yes, in the SP3 file, at the beginning, in the first row, you find this information. So the orbit are fixed. What happened for the point in the Earth? For the point in the Earth, that means this one, you just put a weight, a height weight to the coordinate of the reference system. And at the end, you are going to check using Helmer transformation with 7 parameters, rotation, translation, and scale, if your solution is in agreement with the theoretical solution. Of course, we don't obtain the exact values, but we see that you can control if you have, for a day, if you have a problem in station A, that is a reference station, and that day this station doesn't work well, for instance, is a mountain and is covered by snow. So the observations of this station are not so reliable than the observation, for instance, these stations that are working without any problem. So in this case, if you fix the coordinate of this point, you introduce the error, because we compute the distance. Okay, the orbit are fixed. If you fix this one, the observation have to adjust to fit this. You introduce this in all your network processing. But if you use a network or reference frame, you are going to use this network constraint as a rigid body, and you are going to check how this rigid body fit with the theoretical values. So in this case, if you have this antenna covered by 2 meters snow, you can say, okay, for this day I remove this reference station, because when I check the residual of this adjustment between the observations that we obtain and the theoretical values, I found a very high residual value. So I say, okay, in this day, this station is not reliable, probably because there is a special problem, or also in the processing something goes wrong. Do you remember we have also error for processing? The software completely do a wrong estimation of the ambiguity or something like this. So I've wrote a lot of things. The definition of the data is not based on the condition imposed on single reference station. Rather, the condition acts on the center of mass of the reference site or the mean orientation of the network. So we use this network composed by the station, and we check the center of mass of this, not every single, we don't fix any station. Usually it's sufficient to demand that the body center of the estimated reference coordinate does coincide with the body center of a priori coordinate, non-net translation condition. Because we are going to, is defined introducing orbit parameters fixed to the combined GS product, the advantage of a minimum constraint solution, so the 3 translation solution, Okay, yes. So, sorry, I see that I brought a lot of things, and I was sure that we already, in the first part, I say what I said. We don't fix the coordinate of the reference frame, but we use a weight. But we fix the orbit. And when I say we compute the element transformation between our daily solution, every day I do this with the permanent station, and the theoretical values that we obtain from the ITRF file, it's like a medium. It's like you have two bodies, rigid body, and you want to fit one body to another one. So you say, okay, this fit, but except for this point, and you can remove. It says that when you use, you fix the orbit. So this, you don't have really strain orientation and scale of your network. It's just a little translation, because you just fit something related to the reference frame. It's a 3D spatial network between point on the Earth and satellite on the space. We fix this part, so we don't expect that our network is completely rotated with the theoretical values. It's just a short correction. It means through you just to estimate the translation condition to fit one with each other. It's not a really complete transformation, because I use just this, you fix this parameter, the orbit and the Earth orientation, because in the software you have also to give Earth orientation parameter to be because you have to pass from ITRF system to ITRF frame to Celestial, to the reference frame related to the star, to the Celestial reference frame. We have seen that we have two reference systems.
Excuse me.
Yes.
I don't understand very well the difference between gamut and...
In gamut, you don't fix the orbit. In gamut, you don't fix the orbit, so your network could be really rotated, translated, scale, and you don't fix the orbit any parameter at the last step. At the last step, you have to constrain this reference station, but for a long part of the processing, you just lose constraint, not fix anything. In the GPS, in Bernice, the trace of the orbit and the orientation parameter. So this part is fixed. The coordinate of the reference frame are free, are loosely constrained. So it's all minimum constraint, just okay, no, it was think about the term, but in so a part of your network is just fixed. So you need just this translation to check if you are in the good position or not. But when you check this part, you don't have to apply these parameters that we are going to estimate. It's just to check if your computation is good or not. It's like a test. You say, okay, at the end of my process, day by day, I check my coordinates of the reference station with the theoretical one. We have an agreement. Okay, we don't see any strain residual. Okay, I'm in this reference system. Okay.
Can I ask also, if you want to compare these two methods, these two approaches, I would like to know the cons and pros of these two approaches. I mean, for gamut and for Bernice.
If you see, the scientific community can use one method, another method. For instance, in my institute, INGV, they use all the software. Gamut, Bernice, and gypsies. They are divided in different centers of analysis that are using this, and there are publications I show the comparison of this. Of course, you are not to compare every single values. You have differences because you have numbers, so you have also computation, noisy. But you are going to see, okay, but in terms of velocity, when we have the time series and we are going to estimate velocity, and we use the same method to estimate velocity, we can see that we can have different method. We obtain the same result, and from the literature that I know, I didn't find differences between one method to another method. I think there is yes, Bernese and Gamete are very similar, use the same time observation, double differences, so the methods are more or less the same. You use the same file with a 5 center variation, so on. If you fix the input, you don't. I see every time an agreement. I was interested to check one thing in this, but we can speak. We can talk after. Okay, but it's my curiosity. I'm going to after. And allora, which reference frame is used by GPS community? We have seen that we have different reference frame. We have W has a 84 system, that is the system of the broadcast ephemeridis, and this is a system provided by the control segment of the GPS. We have IGS reference frame or ITRF reference frame. Okay, usually the GPS community use IGS because you have seen in the, if you remember, in the orbit file, there is the position of the satellite are in the IGS reference frame. IGS 05, IGS 14, like now, and so on. And because this reference frame is obtained just analyzing GPS station, so the orbit is obtained by the analysis of the GPS station, not VLBI stations that not control our satellite. So, and the GPS network is a very dense network. This probably now is better. And okay, this was one. Instead of S, they put B to say that it was like the IGS-08 solution, but they removed some stations, so they introduced a new reference frame, but it means S. It's not a good example. But often in the paper, in the geophysical community, you will use ITRS S or F frame because do you remember ITRF is obtained combining different geodetic techniques, GPS, VLBI, SLR, DORIS, and so on. IGS is just for reference frame obtained analyzing GPS data. So it's more consistent with the GPS, but it's obtained just from these techniques. There is parameter to move from IGS to ITRF. Okay, we can move from one frame to another frame. And okay, this is not updated because in 2017, I have to update, we have IGS 14. But I'm going to correct it. And okay, you can change. We have seen when I show you the website of ITRF. Do you remember? Probably in the first lesson, the second one, there was a website where we find information about ITRF, and it's very hot inside, I agree. And you can find parameters, to change a reference frame between ITRF, but also from ITRF IGS. So we can find also this parameter. And these parameters are translation, rotation, scale factor, but we also use the rate of these parameters, the rate of the translation, the scale, and the rotation. So we have 14 parameters, not just 7 parameters. We have also to take into account for the time, also in the definition of the parameters. Okay, this is, we have seen in the website this one. I'll show you. Okay, what time? Oh, 10 minutes. Okay, at the end of this lesson, before we start with the time series analysis, we see what is a RINX file. A RINX file is a format for exchange GPS data. So, a RINX view. So there are probably we have I'm quite sure a new version of the RINX file. So during the time they improved this, changed this version of this format to include, for instance, GLONASS observation, Galileo observation, and so on. So because now we have instruments that are able to receive data from different constellations, from different satellite positioning systems, GPS, GLONASS, Galileo, and so on. For geophysical application at the moment, for my knowledge, we are not mixing all the GNSS observation. One, because for instance Galileo is started a few 1-2 years ago to be complete. Now 1 year ago in the complete configuration. Otherwise, there is differences between one system and another in terms of reference frame. So we need, I think, some time to really put in the same reference frame, to be sure to are working in the same reference frame, from my point of view. For instance, GLONASS, we have GLONASS satellite for a long time, but we didn't use. All these techniques are just used for real-time positioning, but the precision is not so. The required precision is not so high. This is, for instance, a RINX file, so it's an ASCII file. Sorry, the people are talking. And it's an ASCII file, so you can really read this file, and you have the version of the RINX file, who performs this file observation, the company, the type of antenna of the receiver, the type of antenna, you know with none means that without radon, without the protection of the antenna. You can put the antenna height. You have the approximate coordinate. I told you, when you collect data, the receiver writes in the file the approximate coordinate of the point. So you have already, when you process your data, you have just some approximated values for the coordinate. Here you have 4 observations, L1, code 1, L2, P2, and so on. And each column is related to one observation. And in this row there is written the time. It's an old file from 2007, in July 70, and this is the time, 6 in the morning, of course, for minus 30 seconds. The data are collected every 15 minutes. And in each road, you have an observation for each satellite. And these are the number of the satellite. 1, 4, 70, 31. At the beginning, the receiver tracker receives the signal just for satellite. It needs some time to have all the satellite, a few seconds, but okay. So this is the format to exchange data. So in the repository, in the database, where if you look for the raw GPS data, it means not processed time series, you find Varinex data, and this file could be, okay, this is just for GPS. This is an example of file with GPS observation plus GLONASS. So you can see different letter. G means that this is 23 is the number of the GPS satellite. R10 means that R is a GLONASS satellite number 10, and so on. So they improve the quality. It's a Varinex file, so it takes quite a lot of memory. You know, the binary file use less memory in the storage. So it was study a compression, a special compression of this Varinex. So often you have a file with extension D. Sorry, at the beginning, no, I don't know why. So the Varinex file as finished for O mean observation file, D when the observation file is Atanaka compressed. So you have name of file, point, often the year, for instance now in the name you have the day and so on. O mean the Varinex file, D is the compressed file, Atanaka compressed file. And this compressed file using this algorithm could be again compressed with compress of Unix or zip or gzip and so on. And we also have a format to exchange, to share your solution, the result of your processing. I have computed my solution, and my solution, that means a component of the baseline, the covariant matrix, the parameters that I have estimated or I have constrained are written in this file called SYNEX, Solution Independent Exchange Format, because I can, if we are in agreement with the reference frames, with the type of solution, we can mix my solution with your solution and so on. And know we all about the processing, the covariant matrix and so on, allow us to perform another least square adjustment estimation to have a combined solution, for instance. Or we can use this also to combine solution from other techniques, from VLBI, SLR and so on. So we have a format for the data, raw data, where the data that we have from the receiver and from the SYNEX. From the receiver, you don't have Varinex data. You have a file in the binary of this type of receiver. We have to save memory in the receiver because it's small. So the producer use binary, and every receiver has its proper its owner binary format. So when you put in a database that you are going to share with other people, you translate in the Varinex file using some routines that are available. It depends on the receiver. So it's a standard. Everyone can use the data, if you want, of course. Okay.